So with all of these example problems, what I would first recommend doing is look at the denominator and determine which values of your function are not in its domain. And basically, you're asking yourself, when does the denominator equal 0? If you were to plug in any x value, which x value would make this denominator 0? So what plus 9 gives you 0? And you can literally set the denominator equal to 0 and then solve. Or really, we're looking for the x value that cannot take place in this function. So if we subtract 9, we get x is not equal to -9 in the domain of this function. So right away, we know that an x value of -9 is either a vertical asymptote or a removable discontinuity. And so let's look at our function now. So we have that h of x is x squared minus 81 over x plus 9. And to determine if it's a removable discontinuity or a hole in the function, we would need to factor this numerator so that we can see if we can cancel out an x plus 9 in the top and the bottom. So let's start by factoring here, and you might notice that this is a difference of two squares. Namely, if you have, let's say, a squared, let me use a different color for this. If you have a squared minus b squared, then you can factor this into a minus b times a plus b. So it's always the first one minus the second one, ignoring the squares, multiplied by the first one plus the second one. And we can apply that idea here to this numerator. So applying it to the numerator, we have x squared minus 9 squared. You might even write that out a little bit explicitly for yourself. And so let's work down here. This is equal to x minus 9 multiplied by x plus 9. It's the first one ignoring the square minus the second one ignoring the square, and then the first one plus the second one, all divided by x plus 9. Now notice that the x plus 9s can cancel out. So we knew that -9, it's not in the domain, but because we could make this cancellation, this would actually lead to a hole in the graph. And one thing you can always do is check this with your calculator so that you can visually confirm this. So let's get out our graphing calculator. So for this function, let's put it in parentheses in the numerator. So we have x squared minus 81, and then we'll divide by that entire denominator of x plus 9. And let's take a look at this graph. So we'll need to use our standard zoom. So you hit zoom, and then number 6 is standard. And we're still not getting a great picture, so let's zoom out a bit. So zoom 3 is zoom out, and I want to zoom out on the line, so that is a little bit more centered on that. And we do end up with this linear function, so we're not getting a vertical asymptote at -9. In fact, let's hit the trace button and actually plug in -9. And you can see the domain doesn't exist, but what we can do is look at a point right next to that. And so right about here. So if we did have a vertical asymptote, it would be right around this point. But we don't have that since the function would be going up to positive infinity or would be going down to negative infinity. But at this point, it looks like we just have a hole there. And a graphing calculator, it's not going to visually show that hole very well. So what we're mainly looking for is, does it have that vertical asymptote, which it doesn't. So we can conclude that at -9, that is a removable discontinuity, or it's a hole in our graph. Now we just need to look at when x is equal to 9, and you might notice that's when our numerator will be equal to 0. So we know our function is equal to this x minus 9 times x plus 9 over x plus 9. And we could cancel these out, since now we're not looking at when x is -9, so this is just x minus 9 when x is not equal to -9. Like we saw in the graph, it's just a linear function. And if you plug 9 into this, so now let's just do h of 9, we get 9 minus 9, which is 0. And so when the function is equal to 0, that particular x value, that's what we call a 0 of the function, or an x-intercept. So at 9, we have a 0, and at -9, we have this removable discontinuity.